Hello everyone. In this part of the first lecture, we will talk about the types of digital systems and later regarding the different types of the signals. For the digital systems, we have two main types. The first one is when there is no state, and we call those type of digital systems as the combinational logic systems. In this case, the output of the system is a function of the input. So it doesn't matter what has happened in the past. If you provide the same input at any time, you will get the same output, exactly the same output. The second type of the digital systems, on the other hand, are available when we have the state present. So later I will show you what the state is during the course, but for now we just assume that we have something which is called as the state, and we say that the system has memory. It is the output depends on what has happened in the past in Lithium. In this case, we call the digital system as the sequential system. The sequential systems themselves are divided into two main categories: the synchronous sequential systems and asynchronous sequential systems. In the case of synchronous sequential system, the states and the outputs will be updated at discrete times. So at some given discrete time, the state of the system will be able to change. And that's what we have for the synchronous sequential system. On the other hand, for the asynchronous sequential systems, the state and the output could be updated at any time. So the state will not wait for specific times in order to be updated. It can be updated at any time instance. The state itself will be a function of the state and the input, and the output will be a function of the state, or it will be a function of the state and the input in this case. So again, we have two types of digital systems: the combinational logic systems, which are the systems without memory, let's say. They don't remember what has happened in the past, and we will start with this kind of digital systems because they are simpler. And then we have the sequential systems. And for the sequential systems, we have the synchronous sequential systems and asynchronous sequential systems. Later, we will go into details of analyzing and designing all these different kind of digital systems. Here we have an example of a digital system. I think if you go through it, you will guess whether it's a combinational digital system or a sequential one. So here we have a digital counter. The aim of using this digital counter is to count, let's say, the number of the items that have passed in front of a given sensor. So once an item is passing in front of a sensor, a signal is generated, a count-up signal is generated, and it is sent to this digital counter. And at that instant, the value which is stored inside the counter will be increased by 1. So at some point we have this value. Now if we receive another signal at the count up, instead of 4 at the end, we will have 5, and then it will be incremented one by one. And there is also a reset input, which is used in order to reset the value stored inside the counter to 0. So whenever there is usually a rising edge at the reset input, the value will be set to 0. All the digits will become 0. So now we have two inputs, the count up and the reset input. As the output, we have the visual display. So the value that you see here. And here we have the state as the value of the stored digits. Yeah? So when an input comes here at the count up, the value that we have here will be incremented by 1. So it means that the new value, which is the output for us as well, it will depend on the previous value. So it depends on what has happened in the past. And as a result, you can see that the digital counter that we have here is an example of a sequential circuit. It's not a combinational circuit. On the other hand, we know that there are two types for the sequential circuits. the synchronous and asynchronous. If you remember the difference between these two from the previous slide, for the synchronous one, the changes will happen at some discrete values of time for the synchronous system, and for asynchronous system, the values could be updated at any time. And I guess you can see it over here that whenever there is an input provided for the count up, the value will be incremented, and whenever there is an input for the reset, the stored value will be reset to 0. So I guess you can see that this is an example of an asynchronous sequential circuit. Okay, so I hope this example and the previous slide gave you some view of the different cases that we can have for the digital systems. As I mentioned, we will first start with the combinational logic circuits or systems, and then we will move towards the sequential systems as well, and we will consider both synchronous and asynchronous sequential systems. Alright, so now let's have a look into the form of the information which is provided and how our systems will deal with that. So we will talk about the digital abstraction in it. In general, most of the physical variables are in the form of a continuous signal. Examples of the continuous signals are the voltage on a wire, which could be between 0 and 1000 volts, let's say, the frequency of an oscillation, or the position of a mass. So all these values are indeed normally in the continuous form. However, our computers, the digital computers, cannot work with the continuous values. They need to have a digital abstraction of the continuous values in order to be able to process them. So they will consider a discrete subset of the values. Two discrete values that will be considered are the ones in the form of ones and zeros, where 1 usually stands for true, high, and on, and 0 stands for the false, low, and off. So these are indeed 1, true, high, and on are equivalent to each other, and 0, false, low, and off are equivalent to each other usually. The 1 and zeros could be the voltage levels, rotating gears, fluid levels, and so on and so forth. They will indeed represent these kind of signals to us. And the digital circuits that we have, they usually use voltage levels to represent 1 and 0. So in most of the cases, 1 will be represented by the voltage levels between, let's say, 4.5 and 5.5 volts. And 0 will be represented by the voltage level between 0 and 0.5 volt, for example. Again, we will see more details regarding this later. But for now, you just keep in mind that in our digital circuits, the voltage levels will be used in order to represent the 1 and 0. And these 1 and 0 will be stored in bits. A single bit will store a single 1 or 0, and it will be indeed our binary digit. So later we will see that the bits could be combined with each other in order to create a bigger piece of information. But for now, again, keep in mind that the computers will not work directly on the continuous variables. If you have a continuous signal, you would need to convert it into some discrete form, into digital or discrete form. And here you can see how it happens. Yeah? In the case of digital I/O, we'll have, let's say, only two values, which are in the form of on and off, as you see here, or 1 and 0, or high and low, and so on and so forth. While for the analog signals, we will have many values. You can see an example of an analog signal over here, which varies between -200 and 200. And since the computers don't really work on, or they don't really understand the analog signals, they need to convert it into some digital form. So they indeed fake it using the quantization. Quantization is indeed the process of breaking up the analog range into a given number of the bins. And as the number of the bins increases, which determines their resolution, as the number of the bins increases, the accuracy will increase, but at the same time it will require more complex circuitry to implement. And as the number of the bins decreases, the accuracy will decrease, but it will become simpler to implement. For the digital, you can think that we have only like 2 bins, therefore if you just consider 0 and 1 as the value. Over here you can see an example of an analog signal. Over time it is continuous, and here we have it in the quantized form. So you see that in this case we have a given number of the bins, it's not only 2 bins. For a period of time, you see that in the analog form the value is changing, but in the digital form we have it constant. So depending on how much the analog signal changes, we will have a different value for the digitized form in it. We will discuss again regarding this over the course later. Here we have an example of an analog signal indeed, which is represented here by this waveform. It is continuous in value and also it's continuous in time. So you can see that it changes between the minimum value and maximum value that are here and there, and it changes over time continuously. Over here we have the time, and you can see some discrete values of time here. In the digital form, we have 2 modes, the asynchronous and synchronous. When we have the synchronous signal, it changes only at the discrete instances of the time. So here we have the change of the value, then here which happens at this time instance, the value is changed, and so on and so forth. While for the asynchronous case, the changes of the value only depends on the analog signal. So as far as the value of the analog signal is below 0, we have 0 here, and when it goes above 0, we have 1 here. And then here it changes back to 0. At this point it changes back to 1, and so on and so forth. And you can see that the change happens without considering the discrete timing. So that's why it is asynchronous. In this case, the signal is discrete in value and it's continuous in time. So it can change its value at any time. While for the synchronous case, we have the signal discrete in value and also discrete in time. So you can see how the signal could be dealt with in different cases. Alright, so I think that's all for this part of the lecture. Thank you for watching, and see you in the next lecture, which will be the lecture number 2. Thanks again, and bye for now.